Next couple of minutes, I'll give you an overview of the PFAS problem and some of the challenges we need to address as we try to really bring new technologies to bear here. George, you can go ahead and go to the next slide, please. In terms of what these compounds are, it is a very large class of contaminants, and I've put two on this slide using organic chemistry hieroglyphics, PFOA and PFOS. And so if you read the news on these, these are going to be the ones you hear about most often. George, you can go ahead and animate through that to get a couple of bullet points here. These are 8-carbon surfactants that are used historically and even now for fire suppression and in many products. And they've been used for roughly 50 or 60 years. And unfortunately, we now know they are environmentally persistent and bioaccumulative. Go ahead and go 2 more clicks. There you go, George. They are now associated with several negative health effects in humans, including an association with elevated cholesterol, several types of cancers, and other complications in childbearing. And so the issue here, there are several kind of insidious aspects of this problem. First, because many of these compounds do not break down in the environment. They are lurking in places over decades of use. The second is that although there are 2 compounds shown on the slide, there are thousands of these. Many of them are proprietary. And so even figuring out where these have been used and what transformations they are undergoing in the environment and exactly which ones are the most problematic are all important frontline questions. But there's very little doubt we need to remove these almost completely. They show negative health effects down to very, very low concentrations in chronic exposure, down to parts per trillion levels or nanograms per liter. And so that's hard to even conceive of, but often the analogy that's used is a drop in a large swimming pool is not good. So you can go to the next slide, George. Every 6 months or so, the Environmental Working Group and Northeastern University come up with an updated map where in the United States where these compounds are known to be problematic, and there inevitably more dots appear on this map every 6 months. And the purple locations on this map are all military installations, and we'll talk about exactly why that would be the case very soon. And then the blue dots tend to be more industrial sites where there's been either use or historical manufacture of these compounds. And so you see a lot of dots in Michigan, a lot of dots in Delaware, New Jersey. These are common, these are hotbeds of the chemical industry, but also note that those are places where testing has been performed the most as well. And so we're still even getting a handle of this problem in the United States, and it is like this throughout the world as well. This is not just a US problem. Next slide. Okay, just going over a few places where these compounds get into our environment. I mentioned the military installations as well as airports. One of the largest uses of PFAS compounds that continues today, and really it is really, by definition, putting them out into the environment, are these aqueous film-forming foams used to suppress fires, especially aviation fires. and firefighter training. So these PFAS compounds are excellent fire suppressants, but then they infiltrate groundwater or run off into surface water after use. And as I mentioned, they do not really break down at an appropriate rate. And so this is a huge source of PFOS, but really these AFFF formulations are a complex cocktail of PFAS compounds. Next slide, George. Okay, so the ways that these compounds otherwise get into various water resources are very complex. And so there's a lot going on in this slide, and I won't belabor every single way that PFAS gets into these water resources. But within industry, there are several. One has just been inappropriate disposal into waterways, especially historically. But another one that is really coming into greater attention right now is actually through the air. So through smokestacks at these industrial models entering into the air and then being dispersed by wind locally over communities, and then raining down into surface water and ultimately into groundwater. And so this highlights that it's not enough just to have a very good manufacturing process where we stop dumping these compounds inappropriately, as was done for decades. Really, one has to account for these in the future, ideally by limiting PFAS use dramatically, but also in following their propagation through multiple emission mechanisms. Next slide. And then finally, the last one that is really most relevant to this group is starting to think about this in the context of wastewater. And so there are these release mechanisms associated with burying PFAS or PFAS contaminated media, which then inevitably contaminates landfill leachate, which kind of restarts the problem. Wastewater treatment currently does not really address this issue, and so PFAS will go through our wastewater treatment and then end up in the effluent from wastewater plants, but it will also end up in biosolids, and then those are commonly used as fertilizer, and so that's an entry for these compounds into agriculture. And so this is a known problem. It's definitely one that is on the radar of our partners, our wastewater treatment partners in CoWERC. Next slide, George. And so we're going to hear a lot about these challenges and opportunities for the rest of these couple hours we have together. But broadly speaking, what technology needs to do now is first, obviously, we need to be able to sequester PFAS from water. And in the US, our regulatory framework is woefully behind on this issue, and when it does develop further, it likely will be focused largely on PFOA and PFOS, at least at first, and for likely years or longer. And so as we make big capital investments to address this problem, I think it will be an open conversation as to exactly how broad spectrum PFAS removal people are going to be willing to invest in. But it would be very unfortunate to only really go after those two compounds, spend a lot of money, and then not address a problem that we're going to have to tackle eventually. So I define broad spectrum PFAS removal as incredibly important. The effects of impurities in different kinds of water on various removal technologies. So PFAS is usually not the only thing there. We often have benign organic matter at much higher concentrations that can potentially interfere, as well as other ions, and across surface water, groundwater, leachate, wastewater. They're very, very different compositions, and so that may require multiple solutions or solutions to be very robust to those kinds of other effects. We need to do this on a very, very, very large scale, and that's a big part of CoWERC and many people interested in this problem on this call today, is that this needs to be done in drinking water plants and wastewater plants, or these are going to be places where we need to do this inexpensively, but we also need to be able to do this in a very high throughput way. And then finally, the final solution in talking about PFAS destruction, and this is a very, very common question for people working in this area, is what do you do with the PFAS after you've removed it? And so in terms of removal technologies, if one is working in absorbents, if they can be regenerated, that's a potential advantage, but inevitably you're going to create either a solid or a liquid waste stream or waste product that is contaminated with PFAS. And it's becoming more clear now that current ways of burning activated carbon, for example, that are contaminated with PFAS are problematic. It contributes to the problem by putting these things up into the air. And so addressing that and really offering a complete solution from removal all the way to destruction. You really want the fluorine content here to end up as ideally as fluoride ions, much as a benign product. That's really, we won't really consider the problem solved until we have that well established. So I think that sets the stage well for many of the discussions that we're going to have today, and gets us all on the same page. And so I'll stop and turn it back over to Elena to get started with the rest of the workshop.
Great, thank you so much, Will. I actually do want to just take a minute if there's any framing questions. I thought that was a really wonderful overview. I have one, so I'm just going to exercise moderator prerogative and ask. And I know it's a little bit outside the topic. We're talking about removal, but it strikes me that there's this, whole parallel track of alternatives, right? Like alternative chemicals that can be used to address the same critical needs, firefighting, right? Aviation. There's going to be this, and it's kind of spread across multiple industries. So I guess the question is it the same sort of expertise that's needed on this side of the equation, getting removal together, that's also going to help us come up with alternative ways of managing without these compounds in the future?
I think that's a great question, Elena. And it's, there's a lot of chemistry involved on both sides of that equation. The reason that PFAS compounds have stayed in our daily lives, even as we've known either privately or now more publicly that they're problematic, is that they are very unique in terms of their properties. And so they've been very hard to replace. Not impossible. For example, there's some AFFF formulations now that are not organofluorine based, but it's really hard. They have this. These compounds have this dual property of being, they can repel water as coatings, but they can also repel oil, and not many other things can do both of those functions at the same time. And so it's been really, really tempting to use them in products, and as consumers, we like the magic of them, but now we're paying the cost. And unfortunately, at least in my personal opinion, the downside is bigger than the upside for many uses of these things. But a lot of creativity out there on the phase out side, but so far a lot of the replacements have been to replace one PFAS compound with another PFAS compound, and that makes the problem worse, not better.
Mm-hmm. Great, thanks. Do we have any other questions for Will? Feel free to jump in. We have a few minutes. Any other?
I was going to I started writing it in the chat. I guess I'm just going to say it. For your last question, Elena, in the drug industry, for instance, there's a shift towards an LCA approach that's forcing them to look at end-of-life aspects of new drug development. There's talk about that. So I think that for all industries, a shift to that type of paradigm is going to help prevent future situations where we have a chemical that's widely used and tens of years later we discover that it's very harmful.
Yeah, thank you for that. And Hadass, since you've spoken, actually everybody, we did not do a round of introductions in the front, but could you just introduce yourself to the group? And thank you for joining us from Israel this morning.
Sure. My name is Hadass Kiperwas, and I'm a researcher at Mekorot, Israel's water utility, looking mostly at effluent treatment and reuse.
Fantastic. And we'll be hearing more from you later. So thank you so much.